Good morning, good afternoon, good evening. I am the Oracle of Chinemkutu and welcome back. Today we are going to look at two questions and apparently they were both in the Cambridge International AS and A-Level Mathematics 9709 paper 12 for the May-June 2010 examinations. One was question 9 and the other was the question 10. We just numbered them here, question 1 and question 2. I'm going to do them separately, but and present them in two different videos so that it doesn't become too long. And these questions are an application of calculus integration. And they would rather be all of them put in their separate videos without cutting them, because it's a continuous working that results in a particular solution at the end. So cutting the videos into snippets would not be the best thing to present, or the best way of presenting these particular questions. One thing I want you to understand is I present this way. I do not work the questions beforehand and come and try and present with a paper in my hand so I don't make mistakes. I present this way so that we simulate an exam situation whereby you are in the exam and you are seeing the question for the first time, and then you work it out. You try to think from everything that you have learned, what is the best way to approach this particular question and how can I answer this question. And in any question that you will get, there are many different applications that will come in your mind, and you will be at liberty to take the best. The first question had 8 marks, and both questions are actually questions on the area that is bounded by two curves. And a lot of students, when they are doing this, they are not privy to where you apply these ideas. When you develop further and you continue with the mathematics, in my line of work where we build models, we use what we call the ROC AUC, which is the receiver operating curve or area under the curve. And its principle is based on this mathematical principle that you can actually calculate the area bounded by two curves on a Cartesian plane. And we use it to compare models. And the area that we calculate is between the diagonal line and the lift of the model. And the bigger the area, the better the model. And when you go on with the mathematics, you realize that these things are actually applicable in real worldly situations and in real life. Mathematics is everywhere. Everything that you do has got mathematics in it. Whether we speak about it in terms of numbers or not, there is still mathematics. And so mathematics is, in essence, in every subject. So in keeping with our naming convention, we will call this the application of calculus 3 integration. So here we've got a question which is where we've named question 1, That was question 9 in the past examination paper. And it says the diagram shows the curve, which is a quadratic curve. Y is equal to bracket x minus 2 bracket squared, and the line y plus 2x is equal to 7, which interact at points A and B. These are the points where the curve and the line meet. Find the area of the shaded region. This dotted red region is the area we are supposed to calculate. So there are 2 stages to answering this question. The first stage is for you to find the coordinates, especially the x coordinates of the points of interaction, or the points where the curve and the line meet. And then the second stage is to then calculate, using integration, the area that is shaded there. So the first approach is to realize that the points where the curve and the line meet, the coordinates at those points satisfy the equation, both the equation of the line and the equation of the curve. So here we have the curve, which is y is equal to x minus 2 bracket, all bracket squared, and this is a binomial expansion. And the trick to expanding this is not necessarily to put 2 brackets of x minus 2 and then multiplying 1 by 1. Once you are seasoned in dealing with the binomial expansions and mathematics in general, you will see that there is a trick to expanding this. You will say x times x is x squared, and then x times minus 2 is minus 2x times 2 gives you minus 4x, and minus 2 times minus 2 gives you plus 4. So we have expanded that binomial expression to produce the quadratic equation of the curve, and we call that equation 1. Then for the line is y equals y plus 2x equals to 7, which gives us y is equal, we take 2x to the right hand side and it becomes a negative 7 minus 2x, and that is our equation 2. So to find the x coordinates of A and B, the points where the 2 equations interact, we say equation 1 is equal to equation 2 at the points of intersection. So therefore, we have x squared minus 4x plus 4 equals to 7 minus 2x. So we say x squared, bring everything that is on the right hand side to the left hand side, minus 4x plus 2x plus 4 minus 7 equals to 0. In order for us to minimize the use of, to optimize the use of space, I will go up there instead of continuing down, so we can use the board in full. So then we solve this and we have x squared minus 2x minus 3 equals to 0, and we factorize. And the best trick in factorization is to look at the constant term and look at the coefficient of x, and we say for x squared we have x and x, and then what two factors of 3 will give us 2? They are 3 and 1. So we can say 3 and 1. We have a minus 3 there and a minus 2. That means we are subtracting the larger number from the smaller one. So we have a minus at 3 and a plus at 1. Once we have done that, we can solve. So therefore, we have x is equal to 3, or x is equal to minus 1. So basically, if you look at the diagram there, at the graphs, you can see that A is the point where we have x is equal to minus 1, and B is the point where we have x is equal to 3. Then the line y plus 2x is equal to 7 forms the upper bound of the area that we are supposed to calculate, and the curve y is equal to bracket x minus 2 bracket squared forms the lower bound. So then for us to calculate the area, you have to subtract the lower equation from the upper equation. Always remember that it is always the lower equation that is subtracted from the upper equation. If you do the reverse of that, you end up with a negative area, and you get confused in the exam because basically area is not supposed to be negative. So always remember that the upper bound is given by the upper equation and the lower bound is given by the lower equation. So the shaded area equals to, we integrate with respect to x from minus 1 to 3, and we have 7 minus 2x, which is the upper bound, minus bracket x squared minus 4x plus 4, which is the lower bound, and close brackets. And this is equal to integral from minus 1 to 3 bracket 7 minus 2x minus x squared. We remove the inner brackets, and we notice that there is a minus 1 before x squared minus 4x plus 4. And when we open those brackets, we multiply through by minus 1, which gives us, this becomes plus 4x, and that becomes minus 4 brackets. And this is equal to minus 1, 3. And we have the minus x squared minus 2x plus 4x gives us plus 2x, and 7 minus 4 gives us plus 3. And we integrate. When we integrate, we just put the square brackets and remove the integral sign. So we have, remember, integration is the opposite of differentiation. In differentiating, where we multiply by the power and reduce the power by 1, in integration we add 1 to the power, divide by the sum, and then we increase the power by 1. So here we have minus x to the power 3 over 3 plus x to the power 2. This is over 1 because we have said 1, which is the power of x plus 1, that's 2, divided into 2, and the 2 is cancelled out. Then we are remaining with x to the power 2, and for 3 it becomes plus 3x also to the power of 1, and our limits are minus 1 to 3. Then we substitute, starting with 3 into this equation, and then we subtract the same equation after substituting minus 1. So we have here equals to minus 3 to the power 3 is 27 over 3 plus 3 squared is 9 over 1. 3 times 3 plus 9 over 1. We can put closed brackets here, minus close brackets, we substitute minus 1. Minus 1 to the power 3 is minus 1, so this becomes 1 over 3 plus minus 1 squared becomes 1 over 1, minus 1 times 3x, minus 1 times 3 becomes minus 3 over 1. Close bracket and our square brackets. We no longer put the limits because we've already substituted there. So we solve this, and here we have this is equal to bracket minus 9 plus 9 plus 9 minus bracket. Our common denominator there is 3. 3 into 3 is 1 times 1 is 1. Plus 1 into 3 is 3 times 1 is 3. 1 into 3 is 3 times minus 3 minus 9. This is equals to minus 9 plus 9, 0, plus 9 gives us 9, minus 1 plus 3 is 4, minus 9 gives us minus 5. So we can put another bracket there, and we say this is minus 5 over 3. Bracket and close bracket. And this is equal to 9 over 1. You open up the inside brackets, a minus and a minus gives you a plus. So we have plus 5 over 3. And our common denominator is 3. 1 into 3 is 3 times 9 gives you 27. 3 into 3 is 1 times 5 gives you 5, and 27 plus 5 gives you 32. So this is equal to 32 over 3, and area of the shaded part equals to 10 and 2 over 3. And you are done. So the issue is, some authorities would always want you to put squared units for the area. But in most questions on integration and areas bounded by 2 curves, it is suffice to indicate that area is equal to 10 and 2/3. And because we have stated that the area is, then it automatically follows that whatever units that area is in, they are squared units because it's area. So don't panic about whether you have put a squared or not. Leave it like that and you are done. This is 8 marks.